Alright, good day, EIR students. In our last lecture on chapter 15, I started with you on example 1513, which is calculating the voltage regulation efficiency of a real transformer. So I'm going to start it all from the front so you can get the specs and the problem statement from the textbook. So basically what we needed to do there, we begin a transformer, a real transformer. So we have the primary side impedance, we have the excitation branch impedance with the values given in the table. Then we have the secondary impedance, we have a load. The transformer ratings given, 60S transformer, 20 kVA, 2400 to 240. So remember the order in which it's written tells me primary side, secondary side, what the ratings are. Then very important, it tells us that the load connected to the transformer is a rated load and it operates at a power factor of 0.8 lagging, so we'll come back to this. This is very important and we need to find the voltage regulation and the efficiency. Sorry. So first let's just look at what the fact that this is a rated load means. It means two things. So let's just write this down, rated load. Load means two things. Number one is that the load consumes 20 kVA. So the transformer's rating is 20 kVA, and if the load is rated, it's rated according to the transformer rating, so the load is actually consuming 20 kVA at a power factor of 0.8 lagging. Then the second important thing that it says is it means that the load, the voltage at the load terminals, is the rated voltage of the transformer. Now what's the rated voltage of the transformer on the load side? It's 240 volts. But all these values, remember, are in RMS values. So that means we actually have plus minus 240 volts sitting there. Now they're not giving us a reference value, so we're going to make the load voltage is going to be our reference value. That's the first important thing. Why are we going to need this information? We're going to need this information to calculate the load current in just a moment. Right, because we're going to need that current for the efficiency and the voltage regulation calculations. But before we actually do the problem, so what the textbook does is it starts from this point with a load on the secondary side and it calculates I load, calculates the voltage drop, and then eventually brings everything over to the primary side. So I'm not going to do it the way the textbook does it. I'm going to do it in a little bit of a different way, which is usually done. That is by referring everything on the secondary side over to the primary side first before we solve for the regulation and the efficiency. And then you're going to see it works out at exactly the same values. Alright, so step one, just do there, step one, let's refer everything to the primary side. Sorry, just the camera right again. So we're going to put everything over to the primary side. Alright, so let's redraw our circuit for what it will look like then. So the first thing is we're actually going to shift our excitation branch to the front, because remember the current flowing through there is very small, so the effect it has on the circuit is very small. And then we are going to combine the primary and the secondary impedances into R equivalent and X equivalent, and then we're going to have our load, which is still at 20 kVA and power factor equals 0.8 lagging. Right there, so now I've got my transformer terminals over there. So the impedance of the excitation branch, that stays exactly the same, so that's still 15k over here, and just write this 100k over there, so that stays the same. What we need are those two values, so R equivalent, if we go to the equations and you will find it there, is going to be our R1 plus N, now I just need to make sure, N1 over N2 squared R2. So what is R1? Our R1 value there is 3 ohms, so it's 3 plus, what is our turns ratio? The turns ratio N1 over N2 is exactly the same as the voltage ratio, and for this transformer it's 2400 to 240, so it's effectively like saying it's a 10 to 1, but I'm going to write it out as 2400 over 240, so we know it's going to be a 10 to 1 squared, and then the resistance is 0.03. Just want to shift the camera a little bit this side. There we go. Right. So that is going to give us, if you remember, so that's 3 plus 10 over 10 squared is 100 times the 0.03 is another 3 equals 6 ohms for R equivalent. So now we can write on our circuit there, these things are quite, there we go. We can write our 6 ohms over there. Then for X equivalent, it's going to be our X1 plus again then 100, because that's just 100 times X2. So there we have the 6.5 and we have the J 0.7, so it's 6.5 plus 100 times 0.07, so here we end up with J 13.5. So it's J 13.5 in that case. Now for the voltages on our circuit diagram. So earlier we said that the rated voltage for the load is 240 volts, but that was on the secondary side. Now we've moved everything over to the primary side, so now it's not 240 volts that's sitting here across our Z load. Let's make it prime. What we have now, plus minus, is 2400 volts sitting for the load. So we have V load prime equals 2400 angle 0 degrees volts, and we choose 0 degrees as our reference because that's where we're starting to solve the whole thing. Right, so now everything has moved over to the primary side. Let's do step 2. So step 2 is going to be to calculate I load. Right, and this is a very important step, and I am going to make 2 other videos on this as well, how to step by step calculating I load from the given information. So what's important here is we know that it's a 20 kVA 0.8 power factor load, and we know we are sitting at 2400 volts. We need to figure out what is the load current. Why do we need load current? We need that load current to calculate the output power. Well, actually, we don't need to calculate the output power, we only need this. But we need I load so that we can calculate the input voltage on the terminals, and that's going to be our no load voltage, which we're going to need for the voltage regulation calculations. We're also going to need I load so that we can calculate the losses in our transformer, so that we can calculate the input power, so that we can get our efficiency. So either way, this I load that's flowing over there is critical. So how do we calculate that? Well, we start off with knowing that I equals S divided by V. So strictly speaking, we need to take the conjugate of all of that when we're working with complex numbers. So what's our S value? What's our V value? So in this case, if we're going to get rid of the complex, it's S over V, just the magnitudes, and then angle theta I. But now remember, as we said in class, we have the theta power factor equals theta V minus theta I. In other words, with theta V being 0, we know that theta I equals minus theta power factor. And theta power factor, well, let's just write like this, which is minus cos minus 1 power factor, which is minus cos minus 1, 0.8, and that equals 36.87 degrees. So we know what the current angle is. We also know what S is. The rated power of the load is 20 kVA. So that's, I need to write this a little bit bigger so you guys can see. So let's write this as 20,000. And what is the voltage? The voltage, remember we said we're working on the primary side now. So it's 2,400 volts. So it's 2,400. Angle minus 36.87 degrees. So we get a current on the primary side of 8.333333, angles minus 36.87 degree amps. Right, that's for step 2. So now we know what the load current is. The next step, we want to calculate the what do you do first? Yeah, let's do the voltage first. Right. So let's make it step 4. Step 3. Voltage regulation. So from here on, it's pretty much the same procedures in the textbook. So what is voltage regulation? Voltage regulation is what is the no load voltage minus the full load voltage over the full load multiplied by 100%. Full load voltage, we know what that is. The full load voltage is the rated voltage, which is 2,400 volts. So the problem is not finding the full load voltage, the problem is finding the no load voltage. The no load voltage is effectively the supply voltage or the input voltage to the transformer. So remember, as we discussed in class, if we were to disconnect the load, you will not have any voltage drop across Z equivalent. Let's just write our Z equivalent over there. You will have no voltage drop across Z equivalent, which means the input voltage, so let's do V source. So the source voltage or the input voltage will then directly appear across your output, and that will be the no load voltage. So what we need to solve for is Vs in this circuit diagram. Right, and that we're going to do simply with Kirchhoff's voltage law. So we have Vs is what we're looking for. We have the 2,400 volts, and we are looking for our Z equivalent, the voltage drop across Z equivalent. So let's write that equation in terms of the voltage loop law, that Vs must equal I load times Z equivalent plus V load. Right, so I load, we know what that is. It's the 8.3 angle minus 36.87 degrees. Z equivalent from a circuit is 6 plus 13.5, so it's a 6 plus J 13.5, and then our load voltage is the rated voltage, 2,400 angle 0 degrees. And if you're going to punch that into your calculator, so Vs is this, which means that V no load is going to be 2508.2 angle 1.37 degrees volts. Everything in RMS. Right, so this is our no load voltage. So in other words, if we need to supply 2508 volts at the input terminals, so that when the load is connected and it's drawing rated load current, we actually have 2400 volts on the output terminals. Where does the rest of the voltage go? The rest of the voltage is dropped across Z equivalent. So again, I need 2508 volts on the input to get 2400 out. And if I were to disconnect the load, it means there's no load current, which means there's no voltage drop across the Z equivalent, which means that 2508 will appear directly across my output terminals if there is no load. So we have our no load voltage, we have our full load voltage, so we can calculate the voltage regulation. 2508.2 minus the 2400, and you'll notice here, very important, there's no angles involved, it's simply the magnitude. So it's a scalar that we're calculating, so only the magnitudes of the voltage are being used now. Over 2400 times 100%, and that gives us a 4.51% voltage regulation. Right, so that's for the regulation bit. Next step, let's see if we're going to do it in one page. Yes, okay. I see I've got two methods that I want to show you in order to calculate the power. So perhaps let's do it on a new page. So step 4, calculate the efficiency. Alright, so we want efficiency. And what do we need for efficiency? We know that efficiency equals P out over P in times 100%. Right, let's see, it's a bit skewed there. Let's just sort out the camera again. There we go, a bit better. So do we know what P out is? P out in our case is easy. Why so? We know that the load consumes 20 kVA at a 0.8 power factor. We know that P equals S out times power factor. So that is 20 kVA times 0.8, which tells me that P out equals 16 kilowatts. We know output power 16 kilowatts. Next thing that we need is P in. Now this is where the two methods comes in. The one is to say that P in equals P out plus P loss, but it is also equal to Vs Is cos theta power factor. Now what is this VSIS that I'm talking about? We're talking about the current that actually comes in on the input from the source side, and the power factor there angle is not the 0.8 and that you're talking about. The 0.8 is the load power factor. Here we're talking, when you're taking VSIS cos theta power factor, we need to take the angle difference between the source voltage and the source current. So let's do both of those methods. Let's do the P out plus P loss first. I think that's what the textbook also uses, that method. So P loss is two components. So we usually write it as P loss equals, as we mentioned in class, copper losses and then there's the core losses. Copper losses is I squared R losses, but what I squared R losses are we talking about? So that is the loss inside my R equivalent. So for that as well, we need the I load magnitude. So in this case, it's going to be I load squared times R equivalent. Our load current, now again, remember it's magnitude, it's a scalar that we're calculating, so it's only the magnitude of the current that we need now. So that is the 8.33333 squared, and R equivalent is 6, so it's times 6, and then we get how much? I calculated that one. It's 416.6666 watts. So that gives me the copper losses. Then core loss is the loss that is happening, or that's in this section of the circuit. Alright, sorry, I had a bit of an interruption there on a phone call. So we're busy calculating for the voltage regulation and the efficiency, and we're looking at the core losses. So we need to find out what the core losses is. That's happening inside our RC value, the core resistance value that's sitting over here. And for that, we need the supply voltage. So what is the voltage across that resistor, so that we can do a Vs squared over RC. So for P core, what we need is Vs squared over RC. Now what is Vs? We've already calculated Vs in the previous one. There we found that it was 2508 volts. So again, we are only looking for the magnitude. We never include an angle when we're calculating active power. So it's the 2508.2 squared, and then the core resistance there was 100,000 ohms. That gives you not a very big one. Let's write it down. 62.91 watts. Right, so that means our P loss, I'm doing this very elaborately so that you can see step by step what we're busy building here, plus the 62.91. So the total losses in this transformer is 479.58 watts, which is really not a lot. Right, so now we can calculate P in, which is P out plus P loss. P out we know is 16,000 plus the loss of 479.58. So we have 16479.58 watts for the input power. So now we can calculate the efficiency as P out over P in. So P out is the 16 kilowatts there at the top. So 16,000 over 16479.58 times, we want it in percent, and then we get a 97.1% efficiency. Whoops, sorry. We get the 97.1% efficiency. Right, so that's one way to calculate the efficiency. Now, that 62 is in the way now. How do we calculate it, the efficiency, using VSIS cos theta power factor? Right, so let's do it a bit of an alternative. So we already have all the answers we need. Now we have the voltage regulation, we have efficiency, but I just want to show you, perhaps there's a bit of a revision as well. Let's calculate the efficiency using P in that way. So we can also calculate P in equal to VS IS cos theta power factor. Now, maybe I should already mention that you'll see that this way is definitely a bit the longer route to take. So we have Vs, that's sorted. We don't have this power factor angle yet, so we need this Is. As we mentioned, Is is the current coming into those terminals. So the load current flows in this section. I'm just going to take a red pen. So we have a current flowing in this direction, which is our load current, but then we also have a current coming down in our excitation branch. So in order to get Is, I also first need to know what this current is so that we can calculate Kirchhoff's current law at that node. So let's call this our excitation voltage, as it's usually done. So Is equals our excitation voltage plus the load. So yeah, the textbook doesn't use this method, but it's still just circuit analysis. So what is the excitation voltage? Well, looking at the circuit diagram, the excitation current is simply the voltage across this parallel combination. The voltage, and then divide by this parallel combination. So Vs we already have. So we can just write it as Vs over Rc parallel with J xm, the magnetization component. So let's perhaps first calculate that parallel impedance there, which I probably already did somewhere. I just wrote it all out. So my excitation then is, we know the supply voltage. Now we need to remember, now it's calculating current, so now you have to include the angle. So the voltage is 2508.2, angle 1.37 degrees. So where does that voltage come from? It comes right here from when we calculated the voltage regulation in step number 3. We calculated the supply voltage or the no load voltage. Then we need to divide that by Rc, which is 100,000. 100,000 parallel to J 15,000. So obviously that's also going to be a complex number. So if you do the number crunching there, you must get a 0.169 angle minus 80.1 degree amps. Right, so now we can calculate Is as the load current plus the excitation leg. So the load current, we calculated right there at the beginning, is the 8.3333. So it's the 8.3 angle minus 36.87 degrees plus 0.169 angle minus 80.1 degrees. So now you can see the big difference in the magnitudes, 8.3 and 0.169. So as we mentioned in the beginning, the current flowing through this parallel branch is much, much smaller. So this gives you an 457 angle minus 37.65 degrees amps. Right. So we've got Vs, we've got Is. Now we can calculate Pn. So Pn equals the magnitude of Vs multiplied by the magnitude of Is. And here's the important bit. Cosine of the power factor angle, but it's now theta V minus theta I. So in our case, our Vs is the 2508.2 multiplied by the 8.457. Then cosine, the voltage angle is, where's our voltage angle? Is the 1.37 degrees, and the current angle is minus 37.65 degrees. Right, so that's going to become a plus in the end. So if you do that number crunching, you're going to get 16,4 1.80 watts. And if we just double check that quickly with what we've got with PM earlier, we had 16479.58. So it's very, very close, just a bit of rounding. So we finally then calculate the efficiency in this way as 16 over 16.48. Now I'm writing so many kilowatts times 100%, and that should then also give you 97.1% efficiency. Alright, so there's two ways of calculating input power, and then with which you calculate the efficiency after we've calculated the voltage regulation. Alright, that's it.